Hello everyone, hope you are doing very well. Today we are going to discuss the theory part 5 of the chapter Haloalkanes and Haloarenes. So let's begin our today's topic. NCERT chapter 6 Haloalkanes and Haloarenes theory part 5. Today we are going to specifically cover the NCERT section 6.5. This is disclaimer. Objective of today's lecture. After attending this lecture, you will be able to describe the preparation of haloarenes and understand the various reactions that they undergoes. And the topics that we are going to cover today according to the NCERT. First of all, the section 6.5, that is preparation of haloarenes. Then we will also practice some examples 6.3 and 6.4. And then we will also solve the in-text question 6.2 and 6.3. So let's start with our first topic, the section 6.5, preparation of haloarenes. So haloarenes can be majorly prepared by two methods. The first one is from the hydrocarbons by doing the electrophilic substitution reaction, and the second method is from amines by doing the Sandmeyer's reaction. From amines where the nitrogen-hydrogen bond is present, right? So these are the two methods majorly through which we can prepare the haloarenes. We will discuss them one by one. Let's discuss the first part, the first method, that is the preparation of haloarenes from hydrocarbons by the electrophilic substitution. Aryl chlorides. Aryl chlorides means your aromatic ring is connected with the or is bonding with the chlorine, and aryl bromides, that means it is bonding with the bromine. So aryl chlorides and bromides are prepared via electrophilic substitution of the arenes, aromatic rings, and this process requires a Lewis acid as a catalyst, for example FeCl3, FeBr3 or anhydrous AlCl3. Now let's see the example of this method. So let's say you have a benzene ring, that is aromatic ring. Now you are doing its halogenation by reacting it with the chlorine molecule in the presence of FeCl3 and in the dark condition. The dark condition here is very important because in the case of aromatic halides we use dark condition, but if you have seen that, if you have observed, in the case of alkanes, alkyl groups, we have used the UV light, right? It needs UV light for the activation of the chlorine molecule, that process, right? For the functioning of the this reaction and the free radical, you can say for the free radical mechanism of the alkyl halides. Okay, but in the case of aromatic rings, you don't need UV light. This reaction happens in the dark condition in presence of FeCl3, and this chlorine will get substituted on this benzene ring and you will get a chloro substituted benzene plus HCl will be your side product from this in this reaction. FeCl3 here is a catalyst which is a Lewis acid catalyst. Now if we talk about the substituent, so what will be the effect of substituent on the benzene ring? So if any benzene ring have any substituent present on it at either ortho, para or meta position, then how it can affect this electrophilic substitution? So let's say we have at the para position CH3, okay, we have methyl group present on this benzene ring, plus you are reacting this with a halogen molecule in the presence of iron in the dark condition. So the obvious products are the mixture of ortho-halotoluene and para-halotoluene. So you will get ortho-substituted halogen benzene ring and para-substituted halogen benzene ring, right? So you will get these mixtures, the ortho-halotoluene and para-halotoluene, when the halogen molecule will react with this toluene molecule, and this reaction is happening in presence of iron in the dark condition. Okay, so CH3 here is present as a substituent. Okay, so it will direct the incoming you can say electrophile towards the ortho and the para directions to attach at the ortho and para positions on the benzene ring, and you will get the mixture of product, the ortho-halotoluene and para-halotoluene. Ortho and para isomers easily differentiated by their melting points. Now in this reaction, you can easily differentiate the ortho and the para isomers by their melting points, because if you talk about the para halotoluene is more symmetric, and also its physical state is different from the ortho halotoluene. It exists in the solid state in the room temperature, and ortho halotoluene exists as a liquid at the room temperature. So we can easily differentiate the ortho and the para substituted benzene rings, or you can say ortho halotoluene and para halotoluene, or the products ortho and para isomers, easily by their melting points, because their melting points will be different. There is an important note that the reaction with iodine molecule, if you are doing of a benzene ring, this will be reversible. Reversible means it can go in either direction, from reactant to product or product to reactant, and it will require an oxidizing agent to perform, like HNO3 or HiO4, to oxidize the hydrogen iodide present in a reaction mixture formed during the iodination process. So during the iodination process, the HI will get as your side product, right? So for the oxidation of that HI molecule to the iodine molecule, you need an oxidizing agent like HNO3 or HiO4 when you are reacting the benzene ring with the iodine molecule. So this hydrogen iodide reacts with HiO4 oxidized and give us 3 molecules of iodine plus 3 molecules of water. So Hi is converting into an elementary iodine having oxidation state 0, right? So it is oxidizing, and you can say that iodine from -1 going to 0. So the iodine Hi, okay, the Hi molecule is oxidizing to iodine molecule, and you are getting iodine for the which we are going to use as a reactant for the iodination process of the benzene, right? So when you are doing the reaction with the iodine of benzene ring, it will be reversible. That's why you are requiring an oxidizing agent like HNO3 or HiO4, so that it will oxidize the Hi molecule formed during the iodination to the iodine molecule. Fluorocompounds, if you talk about the fluorocompounds means the benzene have the substituent, or the benzene will attach with the fluorine. Fluorocompounds cannot be prepared by this electrophilic substitution method due to the high reactivity of the fluorine. So we have talked about the iodine, that when you are doing the reaction of benzene with the iodine molecule, you require an oxidizing agent. So you will get iodo substituted benzene, and chloro substituted benzene, and bromo substituted benzene you can also prepare through this electrophilic substitution, right? But the fluorocompounds cannot be prepared through this method because fluorine is having high reactivity. It can't form, or it can't bind with the benzene ring to give us fluorobenzene. Let's see the second major method, that is from amines by the Sandmeyer's reaction. Primary aromatic amine dissolved or suspended in the cold aqueous mineral acid with the sodium nitrite, that is NaNO2, to form a diazonium salt. What we are saying, so we take a primary aromatic amine. This is a primary aromatic amine. The nitrogen is connecting with 2 hydrogen, 1 carbon only. Plus, and this is reacting with NaNO2 and dissolving in a cold aqueous mineral acid at a particular temperature range 273 to 278 Kelvin, and you are getting a product which is a benzene diazonium halide, or you can say a diazonium salt, because N2 positive and X negative both are present. So both charges are present. That's why we are calling it as a diazonium salt. So this is how you can convert the primary aromatic amine to a diazonium salt when you react it with sodium nitrite and also dissolve it into a aqueous mineral acid at the temperature range of 0 to you can say 0 to 5 degrees Celsius. Okay. Diazonium salt solution, that is this salt you are getting, is mixed with then cuprous chloride, that is Cu2Cl2, or cuprous bromide, Cu2Br2, to replace the diazonium group, this N2X negative, with the Cl or Br, right? So if you react the diazonium salt with the cuprous chloride, or if you mix this diazonium salt solution with cuprous chloride, you will get a chlorine substituted benzene after the replacement of diazonium group from the diazonium salt. And if you mix the diazonium salt solution with cuprous bromide, then you will get your major product as bromobenzene after the replacement of diazonium group from the diazonium salt. So if you react this diazonium salt with the cuprous halide, where this halide ion is either chloride ion or bromide ion, that means U2X2 is CO2Cl2 or CO2Br2, then you will get a aryl halide where you will get either chlorobenzene or bromobenzene plus N2 gas will be released. Copper salt we are using because it will favor the formation of aryl radical, which will help in the process of this reaction. Okay. For the iodobenzene, now we have seen for chlorobenzene and bromobenzene by this amines by Sandmeyer reaction. For iodobenzene, what you will do, diazonium salt is simply warmed with a potassium iodide solution. So you don't need any extra effort or catalyst for the performance of the reaction of diazonium salt with the you can say iodine, okay, for the preparation of iodobenzene, because you just have to take that diazonium salt solution and simply warm it with a potassium iodide, and after a little shake you will get iodobenzene. No copper salt in this process is needed, as because iodide ion will self act as a nucleophile in this reaction. So you have this diazonium salt, you just have to heat it, or you just have to simply warm it with the potassium iodide solution, and then after a little shaking you will get a iodobenzene as your major product, plus N2 gas will be released. Here the iodine, or you can say no copper salt is needed, because the iodide ion from the potassium iodide will act as a self nucleophile to attack on this benzene ring. Let's see the reactions of benzene diazonium salt. So benzene diazonium salt show different types of reactions. This is our benzene diazonium salt. Benzene is attached with N2, that is N positive triple bond and X negative. Okay, so this is diazonium salt. We have just seen the preparation of chlorobenzene and bromobenzene from the benzene diazonium salt after the reaction of diazonium salt with copper salt, like copper halide, copper bromide and copper chloride. So from the copper bromide you will get bromobenzene, and from the copper chloride reaction with diazonium salt you will get chlorobenzene. Similarly, you can also get the chlorobenzene by the reaction of diazonium salt with HCl in the presence of copper, then you will get a chlorobenzene. And similarly for the bromobenzene, the another process, the reaction of diazonium salt with hydrogen bromide, the halogen acid, in the presence of copper, and you will get a bromobenzene as a major product. Okay, now you can also have the product which is containing carbon nitrogen bond, that is the cyanobenzene or cyanide, benzene cyanide, after the reaction of diazonium salt with copper cyanide. So copper salt reaction with this diazonium salt can give us various products. Now when diazonium salt reacts with H3PO2, you will simply get your benzene ring again. Okay, and diazonium salt when reacts with the sulfuric acid in the aqua solution and you heat it, you will get an alcohol, that is phenol. Okay, so you will get hydroxyl substituted benzene ring, that is a alcohol. And now for the fluorobenzene. Okay, for the fluorobenzene you have to react the diazonium salt with the HbF4 molecule, and you have to heat it, and you will get fluorobenzene as your major product. Okay, remember, by the electrophilic substitution in the very first reaction we have seen the fluorobenzene can't be prepared because of the high reactivity of fluorine, but from the Sandmeyer's reaction by the primary aromatic amine, you can get the fluorobenzene by the reaction of, first of all, the primary aromatic amine you have to convert it into a diazonium salt after the reaction of that with sodium nitrite, and also dissolved it into a cold aqua solution in a specific temperature range. You will get a diazonium salt Then you have to treat the diazonium salt with HbF4 molecule and heat it, and you will get a fluorine substituted benzene, that is fluorobenzene. So these are the various reactions shown by the benzene diazonium salt. Okay, let's solve an example. Example 6.3. It says that identify all the possible monochlorostructural isomers expected to be formed on the free radical monochlorination of this molecule CH3 whole twice CH, CH2, CH3. So what it is asking, that for this given molecule, the molecule formula is given. For this molecule, if you do its free radical monochlorination, then what are the possible monochlorostructural isomers you can expect that you have to tell. So you have given some time, try to solve this question, and then we will see its correct answer. Okay, let's see. So for this example, first of all, we will see the general reaction of free radical monochlorination, that how it will happen. So if you have a alkane, okay, RCH2CH3, okay, and you react this with the chlorine molecule in the presence of UV light, it is necessary, as I said, right, that when you react the alkane with the chlorine molecule, or when you do the halogenation of alkanes, then you need the UV light for the activation of chlorine molecule to convert it into free radicals. So when the reaction, this free radical monochlorination process, you will get your product as RCHClCH3 plus RCH2CH2Cl. Okay, that means 1 chloroalkane and 2 chloroalkane. So in the open structure of the given molecule is this, whose formula is CH3 whole twice CH2CH3, and its name is 2-methylbutane. So for this given 2-methylbutane, in the open structure, if you see, there are 4 different types of hydrogen atoms that are present: HA, HB, HC, and HD. So if you see the structure of 2-methylbutane, so at the second position we have methyl group, and we have 4 carbon parent chain. So we are saying it as 2-methylbutane. Now it is containing 4 different type of hydrogen. The first one is HA, which is present on this carbon, and then HB present on this carbon, and then HC present on this carbon, and HD, which is present in this methyl group and also in the fourth carbon, or you can say first carbon, right? So there are these 4 different types of hydrogen atoms. So these different hydrogen atoms are according to their bond with the carbon and the positions of the carbon. So this carbon is 4th carbon containing all the same type of hydrogens, HA. This carbon is a 3rd carbon containing HB type of hydrogen atoms. The second carbon is having methyl group. Okay, methyl group have HD kind of hydrogen atoms, and also this carbon present at the very first number is also having HD type of hydrogen atom, and the second carbon is also having HC type of hydrogen atom. So these names are according to their reactivity, that which hydrogen will be, if you replace this hydrogen HA, then you will get a different product, and if you replace this HB, then you will get a different product. But if you replace this HB or this HB, you will get same product. So on this basis, we have divided the 4 different kind of hydrogen atoms present in this 2-methylbutane. And so the main reason behind the distribution of that 4 different type of hydrogen atom is replacement of these hydrogen atoms will give the following. So you will observe different results. So if you replace any one of the hydrogen HA from the open structure of 2-methylbutane, then so you have 2-methylbutane. Okay, HA was at this very 4th carbon. Okay, now if you replace one of the HA hydrogen atom and after the reaction of this 2-methyl-butane with chlorine molecule in presence of UV light, you will get 1-chloro-3-methyl-butane, because after the replacement of one hydrogen HA kind from this carbon, the chlorine will attack on this carbon and gives us the product 1-chloro-3-methyl-butane. Okay, after the monochlorination of the 2-methyl-butane. So this one single chlorine atom will attach on this fourth carbon after the replacement of HA kind of hydrogen, and you will get this as a major product. This is the first case. Second case is the replacement of any one hydrogen of HB kind from the open structure of 2-methyl-butane. HB was present at the very third carbon. So in this 2-methyl-butane, the HB was present at this third carbon. These two hydrogens are HB kind. If you replace one of the HB after the reaction of 2-methyl-butane with chlorine molecule in presence of UV light, you will get 2-chloro-3-methyl-butane as your major product. That means at the second position, that means at this carbon you got chlorine after the placement of HB kind of hydrogen atom, and this will be your major product after the monochlorination of 2-methyl-butane. So these are two monochloro structural isomers we have get until now. Now let's see the third case. Third case is for the replacement of any one hydrogen of HC type from the open structure of 2-methyl-butane. The HC was present at this second carbon, that is only this hydrogen is HC. Okay, so when you replace it with the chlorine, you will get 2-chloro-2-methyl-butane as your major product. Okay, so this HC molecule, its HC atom is replaced by the chlorine, and you will get 2-chloro-2-methyl-butane as major product after this chlorination process of 2-methyl-butane. So this is third monochloro structural isomers of you can say of the product you will get after the monochlorination of 2-methyl-butane. Fourth case, replacement of any one hydrogen of HD type from open structure of 2-methyl-butane. So you have this 2-methyl-butane, the HD was present in this CH3 also and this CH3 also. So HD type of hydrogen is removed. Let's say you are removing from this CH3, the HD kind of hydrogen, one of the hydrogen is removed. So when you do the chlorination process, the chlorine will replace this one HD type of hydrogen on this carbon and bond with this carbon, and you will get 1-chloro-2-methyl-butane as your major product. Okay, so this is the fourth structural isomers of the product after the monochlorination of 2-methyl-butane. So we got four different monochloro structural isomers of the product which we will get after the monochlorination of 2-methyl-butane, the given molecule in our example. Let's solve another example. Example 6.4. Example is write the products of the following reactions. So we have given some reactions. The first reaction is between the alkene and HBr. You have to tell the product. Second reaction is again between the alkene. You can say butane plus HCl. Then you have to tell the product. And the third reaction is again the alkene plus HBr in presence of peroxide. So you have to tell the products of these three reactions. You have given some time. Try to solve this question and then we will see the answer. Okay, let's see. So for this example, let's solve the first reaction, the reaction of halogen acid with the alkene. So if you remember, we have studied about this in this chapter. So reaction of halogen acid with the alkene proceeds via Markovnikov addition if there is not any presence of peroxide as a catalyst. So halogen, that is negative ion, the halogen atom will attach to the carbon that is having lesser number of hydrogen atoms. So you have this reactant styrene. The name is styrene. It is reacting with the halogen acid, hydrogen bromide. This negative part, that is bromine, will attach to the carbon having lesser number of hydrogen. the double bonded carbon having lesser number of hydrogen. So these are the two carbons between which the double bond is making. This carbon have two hydrogen, this carbon has only one hydrogen. So the bromine will replace this hydrogen and bond with this carbon, and you will get one bromoethyl benzene as your major product in this reaction. Now let's see the second reaction, the reaction of halogen acid, here in this case hydrogen chloride, with the alkene. Now again this will proceed via Markovnikov addition. No presence of peroxide is there, so halogen atom will attach to the carbon atom having lesser number of hydrogen atoms. So you have this but1-ene reacting with hydrogen chloride. This chlorine will attach to the carbon having lesser hydrogen atoms, the double bond carbon having lesser hydrogen atom, which is this carbon. So chlorine will attach to this carbon and you will get 2-chlorobutane as your major product. In the third reaction, it is happening in the presence of peroxide. Okay, so if it is the case and the reaction is between alkene and halogen acid, the reaction will proceed via anti-Markovnikov addition rule. That means halogen will going to attach to the atom having more number of hydrogen atoms. It is opposite of the Markovnikov addition rule. So you have this 3-phenylprop1-ene bromine. It is reacting with hydrogen bromide, and bromine will react, or bromine will attach to the double bonded carbon containing more hydrogen atoms. So the more hydrogen atom containing carbon is this one, right? So you will get 1-bromo-3-phenylpropane as a major product after the bonding of bromine on this very first carbon. Okay, so anti-Markovnikov addition is the opposite of Markovnikov addition. If Markovnikov addition says that the negative part or the halide ion will attach to the carbon, double bonded carbon containing lesser hydrogen, then anti-Markovnikov addition rule says that the negative part or halogen will attach to that carbon or double bonded carbon containing more hydrogen. Okay, let's see an in-text question now. The in-text question 6.3. The question is, write the structures of different dihalogen derivatives of propane. So you have given some time, try to solve this question and then we will see the correct answer. Okay, let's see. So for this question, we have to understand the dihalogen derivative first, because you have to tell in this question the structures of different dihalogen derivatives of the propane molecule. So any organic compound in which two hydrogen atoms of a hydrocarbon replaced by two halogen atoms, okay, or in simpler words you can say that any organic compound containing more than one halogen atom is the dihalogen derivative compounds. So for example, if you see, we have ethane molecule, right? When it reacts with the chlorine molecule, you will get 1,2-dichloroethane and 1,1-dichloroethane, right? So vicinal dihalide and geminal dihalide. What is the difference? Difference is the position of the chlorine, or you can say the chlorine attaching with the different numbering of carbon. So in the vicinal dihalide, two chlorines are attaching with the adjacent carbons, and in the geminal dihalides, two chlorines are connecting on the same carbon, right? This is the difference, but they both are dihalogen compound. So let's see for the propane molecule. So there are 4 different dihalogen derivatives of propane. The first one, so the structures of these derivatives are shown below. The first one is propane reaction with chlorine, and you will get 1,3-dichloropropane after the attaching of this chlorine at the each terminal carbons. So you will get vicinal dihalide where these chlorines are attaching on the terminal carbons. Okay, this is a dihalogen derivative of propane, the first dihalogen derivative of propane. Second, when propane reacts with chlorine molecule, and you will get a 1,2-dichloropropane. That means now the one of the chlorines changes position. Again, you will get a vicinal dihalide. That means 2 chlorines are attached on the adjacent carbon. Okay, and 2 chlorines are there in this single compound. So this is a dihalogen derivative of propane, the second dihalogen derivative. The third you will obtain after the reaction of propane again with the chlorine molecule. So 1,1-dichloropropane. This is again a gem dihalide. Okay, here we are calling it as geminal dihalide because 2 chlorines, both the chlorine atoms are attaching with the same carbon. Okay, bonding on the same carbon. So this is 1,1-dichloropropane containing 2 halogen atoms in it. So this is third dihalogen derivative of the propane. The fourth one is again the reaction of chlorine molecule and propane, and you will get 2,2-dichloropropane, that is geminal dihalide. That means 2 chlorine molecule or 2 chlorine atoms are connecting on the same carbon, right? So this is a geminal dihalide, 2,2-dichloropropane. So these are the 4 different dihalogen derivatives of propane molecule. Okay, let's see the summary. What are the concepts that we have covered today? First of all, we have discussed about the preparation of haloarenes, and it happens via 2 methods. The first includes for hydrocarbons by doing the electrophilic substitution, where benzene ring when reacts with the chlorine molecule or halogen molecule in presence of FeCl3 as a Lewis acid catalyst in the dark condition, you will get chlorobenzene as your major product plus HCl will be your side product. The second preparation method was from amines by Sandmeyer's reaction. This includes the formation of or you can say preparation of diazonium salt. The step 1 is the preparation of diazonium salt. So primary aromatic amine reacts with sodium nitrite and dissolve in the cold aqueous mineral acid. In some specific temperature range this reaction happens and you will get a diazonium salt or benzene diazonium halide. Okay, that is benzene attached with N2 positive and X negative. Then step 2 of this method is replacement of diazonium salt in presence of copper salt. So you take this diazonium salt, react it with copper halide, and this X halide ion here is chloride ion and bromide ion. So you will get respectively the aryl halide, that is aryl bromide or aryl chloride as a major product, plus N2 gas will be released from the reaction. Now for the preparation of iodobenzene, through this process no copper salt is needed. You just have to take the diazonium salt, little warm it with potassium iodide solution, and after a little shaking you will get iodobenzene as your major product plus N2 gas will be released. These are the methods that we have covered for the preparation of haloarenes. Okay, thank you so much. That's all for today's chemistry session. Thank you.